In this video, we are going to be discussing rationalizing the denominator using Python's SymPy library. First, we'll go through what rationalizing the denominator means and how you would do it if you were to do it by hand. Then, we'll show you how to do this same thing very quickly and easily with Python in any given IDE that you might want to use. In my case, I like to use PyCharm, and as you can see, that's what I have on the screen right now as an example. And then finally, I'll show you the same thing in a little bit more of a specialized environment, SageMath's CoCalc environment. And CoCalc has several advantages over other environments for this kind of task, including that it has some pre-written code in a snippet that you'll just be able to use right away. And we'll talk about how to do it. Also, another advantage is that you can do it right from your own browser and don't have to download a single thing. But first things first, what is rationalizing the denominator? Well, take a look at this first expression that I have saved here. Now, as you can see, this is 1 divided by the square root of 5. This is a perfectly valid mathematical expression. It's a number that exists in the world. But in mathematics, there can be a number of different ways to write the same exact number. And having a square root in the denominator like this is not the best way to write this value. While your computer or calculator may not care about how you write this number, I hate to be the bearer of bad news, but most math conventions we use today predate computers and calculators and assume, perhaps fallaciously, that a human being will be reading your work without the benefit of machines. And when a human being is reading your work, from a teacher grading your homework if you're still in school, to a reader trying to rely on your published work, if you're a mathematician or a scientist, that reader is not necessarily going to get a lot of value out of seeing 1 divided by the square root of 5 on the page, assuming, again, perhaps fallaciously, that they're not going to be using some kind of calculator. And when there's a square root in the denominator, it can be hard for a human to understand, hard to do further operations like adding or subtracting more numbers to do this, again, by hand. And in the real world, we know that's not a real problem because we have computers, we have calculators, but you still shouldn't put this as an answer on your math homework or publish this in your professional work because for better or for worse, it would look sloppy. So if 1 divided by the square root of 5 is not the best way to write this number, then what is? Well, an important concept in mathematics is that we can always multiply any number by 1 and it will equal itself. So we just need to find an expression that is equivalent to 1 that we can multiply this number by and have the result be this 1 divided by radical 5 written in a new way that no longer has the radical 5 in the denominator. So we would do that by multiplying this number, in this case, by the square root of 5 over the square root of 5. And so, as you can see, this is just multiplying it by 1. Square root of 5 over square root of 5 is just another way of writing 1. But you can also see that this resolves our denominator here. Now, the square root of 5 times itself is just going to be 5. And if that's confusing to you, please do take a look at my video on exponents, which goes into that concept a little bit further. And you can see that 1 times the square root of 5, well, anything times 1 is just that thing, so it's going to be square root of 5. So now we have rationalized the denominator because we have turned this expression 1 over radical 5 into a new expression radical 5 over 5, which, to a computer won't matter, but to a human being looks cleaner and for your benefit will look less sloppy. All right. Now, things get a little bit more complicated when you have an expression in the denominator that's a little more complicated than just radical 5, so we'll just kick it into a little bit higher gear by having 1 over 7 plus radical 5 instead. Again, we have this pesky square root of 5, and we want to get rid of it while retaining the same value of our expression. And as you can see in my example, we do this by multiplying it by what's called the conjugate, 7 minus radical 5 in this instance. You might be tempted to do the same thing we had just done and multiplying this by, say, like 7 plus radical 5 over 7 plus radical 5, but that's just not going to work. You'll just end up with more of a mess in the denominator. Rather, you multiply it by the conjugate, and if you do the first, outer, inner, last, and add them all together, what you'll end up with is 44 in your denominator, okay? And then, of course, in your numerator, it's 1 times 7 minus radical 5 is just going to be 7 minus radical 5. So your end result is an expression that's the same value, but written in a cleaner way without a radical in the denominator. And so now that we have some idea of how to do this by hand, how do we avoid ever having to do this by hand? By using Python instead. Well, usually when we do calculations in Python and we throw a number in there like the square root of 5, Python's just going to, convert it into a decimal. So if you just did the normal math module, math.square root of 5, it converts it to this, which is fine and often what you need, but this is one case where it would be much better if Python had just kept that radical 5 as is, or you could think of it as keeping it in a symbolic form so we can continue to manipulate it as radical 5 itself. And to do that, we can use the SymPy library, a very handy library that allows for symbolic mathematics. So in this case, if you wanted to just have the square root of 5, it would keep it as the square root of 5. And so first things first, SymPy, it does not come with Python when you download Python initially. So you do need to install it, and you can do that with pip install SymPy, and as you can see, I was just installing some other stuff, so let's clear that out. And so now what we have, we can do this in your command line. I'm just going to do it in the terminal that comes with PyCharm just to show you as an example, and you type pip space install space, and it's SymPy, S-Y-M-P-Y. Okay, and if you hit enter, and it'll tell me requirement already satisfied because I already have it. But if you don't have it, that might be one way to get it. There are other ways to do it as well, of course. Do take a look at the link to the SymPy website in the description if you're having any trouble at all. Now that we've installed SymPy, what you're going to want to do is import SymPy. And so as you can see, I went back to the console rather than writing a script just for ease of reference. And what we'll do is we'll import SymPy, but give it a nickname, in this case SP, just so we don't have to type SymPy over and over again. So what we're going to type is import SymPy, S-Y-M-P-Y, as SP. Okay, so that's import SymPy, just like how we imported math up here, and you've probably seen this with other kinds of libraries and modules, just like that, but instead we're going to import it as SP so that the computer knows every time we use the word SP, we're going to be referencing that it's what would otherwise be called SymPy. And so now that we've imported SP, SymPy has a very, very handy little shortcut to allow you to initialize a session in SymPy that will give you everything you need to do for the most part, and especially for purposes of this video, everything that you'll need to do. And that's all in one line. It's really one function, and that's SP dot, and remember the SP just means SymPy because that's what we did, and it's already, PyCharm is champing at the bit. It already knows what we're going to type, and it's right, init underscore session with parentheses because it's a function. And so sp.init session, and it will initialize your SymPy session. And so if you hit enter, wow, it already did a lot of stuff. Okay, so what did it do? Well, it did a few things. One, it gave you some, references, and it told you these commands were executed, gives you some things you can type, and importantly for our purposes, it says from SymPy import all. Okay, the star means all, and that means that it imported everything that we might want to use from SymPy, so we can now use it. It sets some symbols, which we're not going to use so much in this video, but it's very helpful otherwise, and it also importantly does init printing, which in essence tells your computer or whatever IDE you're using, whatever method of displaying the output or printing is best use that. So in this case, just in PyCharm without having added anything fancy to it, it's not going to give you anything fancy, as you'll see, but it will certainly be readable. But once we go into CoCalc, you'll see that the default printing, or the fanciest printing that's available in CoCalc, is really very gorgeous. So we'll take a look at that when we get there. All right, so we're in our SymPy session. And just to show you what I was talking about earlier with the square roots staying square roots, if you just do square root of 5, now bear in mind that's not the math.square root of 5 that we did up here. This is the SymPy square root of 5, which we imported when we imported everything from SymPy, okay? So if we're going to do just the square root of 5 and hit enter, as you see, it keeps it in a symbolic form, square root of 5. It does not convert it to a decimal. Perfect. Now on to rationalizing the denominator in SymPy. When we deal with very basic expressions, SymPy will make some effort to simplify them for you without you even asking. So for example, if we type the square root of 40, it's actually going to give you 2 radical 10. It's not going to put radical 40, like a radical sign and then a 40, okay? And that makes sense. The square root of 40 is the same as the square root of 4 times the square root of 10, so that would be 2 times the square root of 10. So it'll simplify it for you in a way that looks more professional, that's easier to read. It's what someone reading your work would expect to see. They wouldn't expect to see a square root of 40. The same is true for basic expressions that you want to rationalize when there's just one radical in the denominator. SymPy will try to simplify that for you. So when we looked at the expression that we had before, 1 divided by radical 5, which in this case would be 1 over sqrt 5 in parentheses, all right? If we type that in to our SymPy session, what's the output? Well, it's radical 5 over 5, which we saw before was exactly what we expected to see, radical 5 over 5. We didn't have to go through the motions of asking it to do something for us, it just did it. But here's where things get a little harder. What about our second example, 1 divided by the square root of 7 plus 5? 1 divided by 7 plus the square root of 5, rather. Though what I just said also would have been a similar example, but actually the example is 1 over 7 plus the square root of 5. Okay, well, if we just type that into SymPy with nothing else, 1 over 7 plus the square root of 5, and it would be typed like this, okay, with the square sqrt 5 in parentheses. No, it did not rationalize the denominator, 1 over radical 5 plus 7, okay? And we get what we gave, just 1 over radical 5 plus 7. Our teacher's going to dock us points for sure. Oh no, well, not so fast. SymPy has one more trick up its sleeve, and that's the function radsimp, okay? Radsimp, spelled like this, R-A-D-S-I-M-P, presumably short for radical simplification or something to that effect. And recall, we already imported everything from SymPy when we initialized our session, so there's no need to separately import radsimp. We already have it. So we type radsimp with these parentheses, and then we can type in our expression. So inside these parentheses, let's do the same exact thing we did up there, 1 over 7 plus the square root of 5. And hit enter. Now it's 7 minus radical 5 over 44. Survey says that is exactly what we expected to see when we did this same thing by hand, okay? So that's really nice, and it rationalized the denominator for us. No tedious math by hand required. One last note, there is a caveat in the SymPy documentation, the link to which is in the description, that I do want to share with you, though I'm not going to dwell on it. One thing that SymPy can be used for is manipulating symbols like X, Y, Z, and you can use those symbols in your expressions, and SymPy will retain it. So if we do square root of X, square root of T, and of course, remember, we imported these. We set these symbols already when we initialized the session. These didn't just come from nowhere. It's just something automatic that happened. when you initialize the session. And so, if you were to do rationalizing the denominator with radsimp with these symbols, like, like T or something, it might not give you something that's exactly accurate. It won't necessarily be equivalent to what you had before if you were to plug in all of the symbols with any given value. So do be careful. You can do something called turning symbolic to false with a keyword argument that would prevent it from rationalizing the denominator at all when it has symbols, but that's a little more advanced than I want to get into with this tutorial. But do take a look at the documentation in the description for more detail on that. All right. So this is all well and good if you're going to do this in any given IDE like PyCharm. But what if we wanted to do this in a little bit more of a specialized environment and from the comfort of our web browser to boot? Well, we can do this same thing in use online in a website that's put out by SageMath called CoCalc, and that's a terrific open source math platform. It lives in the cloud, and you don't need to make an account or anything. It's really nice. So to do that, let's go there now. I'll just start up Chrome here. And so to do this, you can just go to CoCalc.com. All right. You can also find the link on the SageMath website. Okay, so CoCalc.com. And there's different things you can do. You can certainly log in, make an account, save your work, but you don't need to, and we're not going to for purposes of this video. We're just going to click Run CoCalc now. And as you can see, it's loading some things. So give it a few seconds. And then once it loads, it's going to ask us, hey, what programming language do you want to use? And of course, we're going to pick Python 3. So here it is. It says select a kernel. And it'll give you a bunch of options. If we scroll down, there's some great ones. There's Julia, there's R, SageMath, which for long-time viewers know I love, but of course, and there's more if you scroll down, but of course, this is a Python 3 video, so we are going to be clicking Python 3. And now it gives this to you in a Jupyter notebook, okay? And a Jupyter notebook is just a means of writing code in kind of blocks. They're called cells, and that's all fine. I'm pretty zoomed in right now, just for the benefit of those of you watching maybe on a phone, but I'll try to make this as viewable as possible, even though we'll be going a little bit into a couple other things here. So the nice thing about CoCalc is that it takes everything that we did before and it actually lets you write in with these things called snippets. And it has these snippets, which I'm actually, you know what, I'm just going to reset this to 100. Hopefully you guys can see it. If not, let me know in the comments and I can try to re-record it. Okay, so it has these snippets, and these are really nice. These are kind of pre-made code that someone else came up with and is free for you to use. And you just click snippets like I did before, so I'll show you that one more time. There's a little button here called snippets. It says show code snippets when you hover your mouse. You click it, and then it has a search bar, and sometimes it takes you a few tries. It took me a few tries to find exactly what it was that I wanted to do, because I was searching for things like rationalize the denominator, but it's actually in a little bit more plain English. It's remove square roots from the denominator. You know, what actually I think ultimately worked for me is I typed in denominator, and then it came up. But you see, I mean, there's a bunch. We're going to join over common denominator, cool things. But what we're going to do is remove square roots of the denominator. Just click that. Okay, and now you see there's some pre-made code here for you. And the nice thing about this is you see it's not having you initialize a session in SymPy like we did before, but it does something similar. It, imports everything. It sets some symbols because it doesn't know exactly what you're going to do. It makes a variable called expr, short for expression, and then it has you do the radsimp of the expression. Okay, so let's do it. If you've already done something like imported everything from SymPy, because say you've been doing a lot of stuff in SymPy and you've already written all this pre-code, you can click the setup code to not include that and just include the rationalizing the denominator part. But we do want that, so we're going to click setup code, and then we're going to insert the code, and here it is. All right, and so now what you can see is it has set this as just some random expression, but we don't need that. We can just use our own example. So under expression, you can just type whatever it is you wanted to do. And our example before, which we can keep, is 1/7 plus the square root of 5. And I'm just keeping it simple, but you can see how you can type in much more complicated expressions here, of course, as well. And then to run this, it's a Jupyter notebook, so it can run cell by cell, but we're actually, in this instance, going to run all the cells. So you just do cell from the cell menu here, and then run all. Okay, and nothing happened. Why did nothing happen? Well, because all we did was we set it equal to a variable. We haven't printed our expression. We're just storing it in our variable called expression. So, it's nice we didn't get any errors thrown, but we do need to print our expression, and there's a couple of ways you can do this. You could do print expression like that, print with your variable if you wanted to, but you actually don't need to do that. You can just do expr, just write the name of the variable in, and it should work for you just fine in this kind of Jupyter Notebook environment. So let's run all, and this time it happened. And there it is, looks really good. Let's try zooming in a little. And you see how nice that looks. It looks really pretty. It's printed out like that in a really, really gorgeous way. So that's kind of it for rationalizing the denominator. Once you have this code set up, you can certainly copy paste it, or if you want to do a bunch of these, or you can write anything you want here inside, just to be stored inside expression, and it'll work for you just fine. So now I turn it over to you guys to try this out yourself, and do let me know how it goes in the comments. So this has been rationalizing the denominator, first by hand, which of course was awful, then with SymPy in any given IDE by initializing a SymPy session, and then finally in the more specialized CoCalc environment from the good people at SageMath. The link to all of this will be in the description. Thanks very much for watching.